In this section of chapter 8, we will talk about periodic properties, and periodic properties have to do with the periodic table, of course. And so what are we going to do? First, let me just remind you that you have done a little bit of classification of periodic table. Actually, you've done quite an extensive classification of periodic table in metals, non-metals, transition metals. You've learned about group names of the periodic table. And then we also just finished electronic configuration, so you know how it's divided into S block, P block, D block, and all that, right? So everything you know. You also know the periodic table is arranged according to atomic number, not mass number. One of the trends that Mendeleev actually saw in the periodic table early on was some of the chemical properties. So all the group members have similar chemical properties, and then he was also able to predict some of the physical properties in there. In this chapter, or in this portion, we will talk a little bit more about some other properties which we have not addressed yet, and they do have trends in the periodic table. So we will talk about atomic radii, ionization energy, electron affinity, and then one of the other trends we'll talk about is also the metallic nature, because as we know, the periodic table is divided into metals, non-metals, and then there's the transition metals, which are also metals, but there is the metalloids also. Okay, so we'll talk about all of these. One of the things that I would like you to remember with the periodic properties is that we are going to be dealing with only the main group elements. Okay, we are not talking about transition metals. Remember what happens when you're dealing with transition metals. The electrons are going into the core. Okay, when you're dealing with the main group elements, all the electrons that you're adding on, they're all going in the valence. If you're taking out electrons, you're doing valence electrons. Adding electrons, valence shell. So everything is about valence shell and valence electrons in the periodic properties. Transition metals don't do that, right? Transition metals, everything, all the electrons are going into the core. And lanthanides and actinides also don't follow these trends. Okay, so we are going to limit this to main group elements. All right, so before we get into all the other periodic properties, I want to talk about something called the effective nuclear charge. And I think once you understand the effective nuclear charge, it will be easier for you to understand all other properties that I'm explaining to you. Okay, so what is effective nuclear charge? Effective nuclear charge is the attraction of valence electrons, and for me, my shorthand is VE for valence electrons, to the positive nucleus. Okay, so which means valence electron, meaning that's the valence shell. So which means we're talking about the outermost shell and its attraction to the nucleus. The valence shell can be the first shell, or it could be the fifth shell, right? Depending on which kind of element you're talking about. So the general trend for effective nuclear charge is that effective nuclear charge increases as you go to the right and decreases as you go down. And that is how we look at the trends. Now, I'm going to leave the transition metals in there, but please note that just because it's there in there doesn't mean we are covering the trends, okay, of the transition metals. I just leave it because it's kind of nice to see the periodic table as you know it. Okay, anyhow, so increasing effective nuclear charge, decreasing. All right, that's the trend. Now let's talk about why. So we have two things to talk about. When we talk about trends, one is going across, which is in a row, and then one in a group, which is going down. Okay, so first let's deal with this. Now I'm going to explain this to you so you don't have to read it, and I'm not going to read this. I mean, you can if you want to with me, but otherwise I'm going to use the diagram to explain to you how the effective nuclear charge is working. Okay, so I'm going to take two elements in a row, because remember we're talking about the trend in a row. So here is beryllium, and then here is carbon. This is the electronic configuration, and what I've underlined here are the valence electrons. So in beryllium you have 2 valence electrons, in carbon you have 4 valence electrons. The valence shell is the red one, the core is the blue one. Okay, and of course you have the protons in the middle. It has nothing to do with the neutrons. Neutrons don't have any charge, okay? So it's just about the protons and the valence electrons. So here you have 4 protons pulling in 2 electrons, and here you have 6 protons pulling in 4 electrons. Now remember, the protons are all in the same location. However, the electrons are distributed in the core and the valence, okay? But protons are all in the same place in the nucleus. So the 4 electrons that we have for carbon, they are being pulled by 6 protons, whereas in beryllium, there are 2 electrons in the valence shell, they are being pulled by 4. So the attraction between 6 protons and 4 is a lot more than 4:2. And so carbon has higher effective nuclear charge. And that is the trend in the row, which means as you go to the right, then effective nuclear charge increases. Now let's look in the group, okay, as you're going down. So now we're going to look at beryllium again, just because, and then we will look also at magnesium. So beryllium, same electronic configuration, 2 shells, one is the valence, one is the core, 4 protons. Looking at magnesium, which has now 12 protons, and now it has 2 core and then 1 valence shell, right? Again, because these are in the same group, and in the valence then you have 2 electrons, right? Because they're in the same group in group number 2, so group 2 has 2 valence electrons. But what happens now is that in beryllium, the 4 protons, they're pulling into the 2 electrons. There's only 1 shell in the middle with the core. But in the case of magnesium, the valence shell is too far away for the 12 protons. So even though there are 12 protons, the valence shell is too far because of the 2 core the 2 core shells, okay, that are in there. So because of that, the beryllium ends up having a higher effective nuclear charge. Okay, so the valence shell in magnesium is too far away for the protons to pull the valence electrons. Now, one thing you might remember when we studied the quantum structure of the atom is I said to you that I may draw these shells like as if they're uniform, but they're not equidistant, okay, from each other. Some of them are farther away from the nucleus. So the valence shell is not equidistant like this, okay? The distance between them are different. So the valence shell is really far away actually from the nucleus. That's what I'm trying to say. So anyhow, what's happening here, okay? One of the things you need to remember that in the trend in a row, the electrons are being added to the same valence shell, right? So here also in beryllium, it was the second shell. Carbon also is the second shell. But as you go down a group, you're actually adding another shell and then another shell and then another shell, okay? So that's kind of how it works. So which means that the valence shell is getting farther and farther away from the nucleus. So the attraction between the protons and the electrons get less and less. Okay, and so therefore the higher effective nuclear charge is on the top, and as you go down, the effective nuclear charge decreases. Now, what's the whole point of learning about this? Okay, because when we look at the 3 properties that we are going to study, the ionization energy, atomic radii, and electron affinity, that has to do with the valence shell also and the nucleus. Okay, so when I talk about those, then all you need to think about is the attraction between the nucleus and the valence shell, and that will help you, okay, understand those properties also, okay? So again, the attraction between the protons and the valence electrons, that's what's the key thing. So here are the 4 things that again we're going to talk about. Atomic radii, which is half the distance between the 2 nuclei next to each other. That is how atomic radius is measured because it's too tiny also, right? So atomic radii is actually measured in angstrom, which is 10 to the negative 10. Nano is 10 to the negative 9. Angstrom is 10 to the negative 10. Anyway, and then ionization energy is the amount of energy required to remove an electron from an atom in gas phase. So ionization is like forming a cation. Okay, that's what this is. Electron affinity is the amount of energy given off when an electron is added, or just the change also. And metallic character, of course, is anything that behaves like a metal, right? We've talked about that. We'll talk about it again. So let's deal with the first one, okay, which is the atomic radii. And as we said, atomic radii is half the distance between two nuclei next to each other. So if you just can imagine, you know, a whole bunch of soccer balls next to each other, then in the middle, you know, the distance between them, half of that is the atomic radii. Okay, so the general trend is that as you go across the periodic table, the radii decreases. As you go down, the radii increases. Now, you can imagine why the radii would increase even without knowing anything, is because as you go down, you keep adding a shell, right? So it's almost uh, very logical to think, yeah, if you're going to keep adding a shell, you are definitely going to increase the atomic radii, all right? But why does it decrease as you go across? And that's explained by effective nuclear charge. So here is the little pictorial, okay, for us to see, so you can, kind of visualize, okay, what's going on here. So for any group, as you go down, for any group, as you go down, the radii is going to increase, okay. Again, why? Because the shell number has added, okay, in there. There's a new shell, there's a new shell. Now, as you go across the group though, across the row, then what's happening? You're adding electrons to the same valence shell. So if you're adding electrons to the same valence shell as you're going to the right, then you're increasing the effective nuclear charge, which is the attraction of electrons to the protons. So it keeps shrinking and shrinking because the attraction gets more and more. And because of that, the atomic radii decreases, okay? So small, smaller, then boom, it gets larger, all right? Because you've added a new shell. Small, 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 smallest, and then again, you added another shell, so it got larger, okay? And then again, gets smaller, 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 and then again, you added another shell. So you can see the trend, okay? And look here with the transition metals. This is why we don't study transition metals, so the lanthanides and actinides, is because their nuclei, their atomic radii is almost the same because everything is in core, okay? So even though it's given to you, you can still ignore it if you want to. Actually, I insist you go ahead and ignore it. Okay, so here is a problem for atomic radii, and refer to the periodic table. Definitely refer to the periodic table. In fact, you should be sitting with a periodic table, so I hope you have one with you. So keep one handy, and then we're looking at three elements here: bromine, selenium, and tellurium. And what I did here is I gave all those three of you from the three elements kind of sort of diagonal to each other also, okay, and sort of, you know, kind of together, because a trend you can see, okay, and so this is also a trend that you're looking at, but you're also comparing these two. So here is the trend for selenium and bromine, that as you go to the right, the atomic radii is going to decrease, but as you go to down the group, it's going to increase. Okay, that's kind of what the trend is, and that's all really that you need to look at. So tellurium is larger than selenium, and then selenium is larger than bromine. And once you know the relationship between those, then you have your answer. Tellurium is the largest one, okay, and bromine is going to be the smallest one then, okay. Here's another one with arsenic, bromine, and antimony. Sp is antimony. Yes, I didn't ask you to memorize that, but you know, antimony, who doesn't know Sp? Okay, so here we are, and antimony is below arsenic, and then bromine is a little bit farther away. So this also should be easy enough for us to do, because bromine should be smaller than arsenic, and then antimony should be larger than arsenic. Okay, so once we know all of that, then there we go, arsenic is larger than bromine, then we can put our trend. Okay, so antimony is still larger. My rule generally is that if you have something below, that's going to be larger in general. Okay, if you have anything below, it's going to be larger, and then if you have anything on the right side, that's definitely smaller, right? That's the trend. Okay, let's look at ionization energy. Ionization energy is the energy required to remove one electron from an atom in a gas phase. Now, the gas phase is an important part here, okay, because you don't want the energy of going from solid to liquid also count, okay? So you want to start from a uniform space, which is, or uniform phase, and that's the gas phase, okay? And so you're removing an electron. Now, removing an electron can be the first electron that you're removing or the second, okay? And that is something we have to indicate. If something says, a question says, what's the ionization energy trend? That is just the first ionization energy trend, okay? But then if this is what is the second ionization energy trend, then that's the second one, okay? All right. So now, without reading any of this, okay, let's just talk about this, okay, for a second. Ionization energy is the energy required to remove an electron. How will it be harder to remove an electron? It will be harder to remove an electron if an electron is attracted too much to the nucleus. And how is it attracted to the nucleus as you go to the right? Yes, because you're adding electrons to the same valence shell. So if you're adding electrons to the same valence shell, then the effective nuclear charge is more. If the effective nuclear charge is more, it's going to be harder to remove an electron. On the other hand, once you go down a group, going down the group, you're adding a valence shell. That valence shell is now farther away from the protons, so it's going to be easier to remove that electron. Okay, so there you go, your trend. Ionization energy increases as you go to the right and decreases as you go down a group. So this is it, okay? And again, remember what you're looking at. You're looking at effective nuclear charge. Effective nuclear charge is increasing, ionization energy is also increasing here, okay? That's how we are looking at all of this. So I'm trying to write the effective nuclear charge also so you can see the relationship, okay, between the two. Okay, so I think here, yeah, I have a graph also, okay? So ionization energy increases as you go across the row. Boom, it comes down when you start a new shell, and then ionization energy increases again, and then it is low again for the next one. So you can see actually all the metals are here, okay? Because metals will give their electron easily. Why? Because the effective nuclear charge is not that much. And look, all the noble gases are here on the top, which is the group number 8. And that's because it's very hard to remove an electron from there. Why? Because those electrons are highly attracted to the nucleus, okay? Because they're all adding on to the same shell. Whereas in all the metals, you've added a new shell, okay, in there. So ionization energy is definitely lower for the metals and higher for the non-metals. So here's the ionization energy for second, third, and fourth ionization energies, okay, like electrons. So the thing that I want to show you here, okay, is that the first ionization energy can be small or high depending on the element. But as you go to the second one is always going to be higher, first of all, okay? So all second ionization energies are higher. Why? Because now you have fewer electrons but still the same number of protons. So the effective nuclear charge increases. But what I want you to see here for really interesting data is look at lithium. Lithium is first ionization energy is 520. The next one, look at this. Oh my God. Okay, 7200. I mean, that's, or 73, you can say 7300. It's way too high. What happened here? So lithium has two shells, shell number 1, shell number 2. You removed one electron from shell number 2. So now it means that the shell number 1 is now the valence shell, which has the 2 electrons. Now that is much closer to the nuclei, so it becomes really hard to remove the second electron, okay? And the line that I have drawn here shows you that distinction. So in beryllium, you have the 2 electrons in the valence shell. Beryllium is in group 2, so 2 valence electrons. After those 2 electrons are gone, the whole shell is gone. Okay, it's not gone, but it's not there. There's no electron there anymore. So which means that the third ionization energy becomes really high, okay, at this point. And look, it's even higher than lithium. Why is it higher than lithium? Because beryllium has more protons than lithium, okay. So just look at these, the step that I've drawn for you here, which shows you that now you're removing the electron from after all the valence electrons are gone initially, okay. So that's how the ionization energy changes. And the second one definitely is going to be higher, okay? But the second ionization energy for lithium, way higher than that for beryllium, okay, for sure. So you should be able to predict that also, okay? You should be able to look at the number of protons and look at the number of electrons, see if they have the valence shell or not, and then see which one is going to have a second high ionization energy, okay? Compare the second and the third ionization energy also. It's just a matter of effective nuclear charge, okay? Just look at the number of electrons, look at the number of protons. That's it. Well, and the attraction between them. Okay, so here is another problem then for ionization energy, and here we have bromine, oh, same elements, bromine, selenium, and then tellurium. So yeah, tellurium definitely going to have lower ionization energy because it is down here. Bromine is going to have higher ionization energy. Selenium is kind of stuck in the middle again. Okay, so tellurium is lower than selenium, and bromine is, our selenium is lower than bromine. Bromine is higher. Okay, so there is your trend. Bromine is the highest, tellurium is the least. Okay, and here we are looking at arsenic, krypton, and K. So krypton is noble gas. I can just shut my eyes and say this is going to be the highest, okay, for ionization energy. Potassium, I know, is a metal, and that should be the lowest, okay, in there. So let's go ahead and see, lower than arsenic. And arsenic is lower than krypton because krypton is on the right hand side, right? So krypton is going to be the highest, potassium is going to be the lowest. Follow the trends. Electron affinity is the measure of energy released when an electron is added to a valence shell. Now you can look at the energy, but the problem is that you are not going to be given these energies, okay, in there. So for the trend, you need to remember this one, that electron affinity increases as you go to the right and decreases as you go down, okay. Now I can explain the electron affinity to you in certain ways, as in stability. So when you add one electron, okay, to fluorine, for example, this becomes very stable. So which means all the instability energy is gone now. And fluorine by itself was very unstable, so it was very high energy. And all that energy is now lost when it gains an electron, okay? You can think of it that way if you want to, okay? So all the halogens are like that, okay? All halogens are like that because they are unstable, and as soon as they gain an electron, they become more stable. Now, if you don't want to think like that, and not that I'm telling you to think like this, but the easier way to think of it is, which element likes to have electrons? And we know already that the non-metals like to gain electrons, okay? So if you want to think of affinity just in terms of what English word is, you know, affinity, which means it likes electrons, well, there you go. That's your trend then, okay? So all the non-metals, they like electrons, and then here you can just say decreasing, okay? Electron affinity. Actually, metals don't have anything to do with this. So metals should not even be part of it, but it is still a trend because if you look at fluorine, chlorine, bromine, iodine, you should still be able to decide within that group what is happening. So electron affinity decreases as you go down. Now, halogen is not a good group for talking about stability, because all of halogens are diatomics, if you remember, okay? And what the diatomic tells you that is the single atom is not very stable, okay, whether it's F or Br or I, it's not, it's I2 Br2 and all that, right? So which means it's forming a compound even with itself, okay? It doesn't want to be by itself. But then when you come down here, to some of these middle elements, they can exist on their own. Like, you know, tin can exist on its own, lead can exist on its own. Okay, so by the time we come to these ones, then you can see, oh, okay, now I can see how electron affinity is decreasing. So even though carbon can exist on its own, but carbon forms a lot of compounds. Okay, so it likes having electrons, but then that kind of a feature decreases as you go down. Okay, so lead is really not interested in bonding. It's pretty much like the noble elements, like leave me alone, okay, kind of a thing. So, but anyhow, so that's the trend for electron affinity. For the metallic character, you have to remember the properties of metals. Okay, and so here are the metallic properties. So once you know what the metallic character is, the non-metals are a little bit opposite of that. Okay, so for example, metals are shiny, may not be shiny. Non-metals, they're good conductors of heat and electricity. Non-metals, not so much. Okay, metals are hard, non-metals are not. The metals form cations. Non-metals don't form cations, they form anions. Okay, and then one of the properties that I'm going to add on here is that with the metals, you know, or I've added on here, excuse me, is that they form basic compounds. Okay, and we'll talk about that later. And that's also a very important kind of a property of metals, is that when you form oxides of metals and you dissolve it in water, then you will get bases. Okay, non-metals on the other hand will give you acids. Okay, that they form acids in general. And then you have metalloids. So metalloids kind of behave both like metals and non-metals. All right, so these are a little bit different. So how do we define metallic character on the periodic table? Metallic character decreases as you go to the right and increases as you go down. Okay, that's how metallic character works. So even in the non-metals, sometimes the right side of the periodic table, when you get to the bottom, then you find metals in there because the metallic character increases as you go down. Okay, a group. So that's how it works. All right. Okay, oh, here is electron affinity and metallic character question. I was wondering, I'm like, where is that question gone? I thought I had it. Okay, here we are. So arrange according to electron affinity. Again, we have those three elements, bromine, selenium, and tellurium. So tellurium, lower electron affinity, bromine is higher, so selenium is still in the middle. Okay, with that, so here we go. And tellurium is less than selenium, and so our electron affinity is the highest for bromine and least for tellurium. Metallic character, you can look at arsenic, bromine, and antimony. So whatever is going to be down here, okay, the lowest element, that's going to be the most metallic. Whatever is on the right is going to be the least metallic. Okay, that's how it works out. So here is my step-by-step answer, okay, for you. So antimony is going to be the most metallic. So here are all your trends in one table, okay, and you can read this on your own. I'm not going to do this, okay, because this is way too much for me to read for you, but these are all the trends that we have talked about. So I've given it to you according to groups and rows. So across this should be a row, not a group, across a row and then down a group, okay, what the definition is. Then let's talk just a little bit about ionic radii, okay, because ionic radii is just a slightly different thing than atomic radii. When you have a cation, you've lost electrons, not you. You are not a cation. So when there is a cation, it has lost electrons. Once it loses electrons, number one, it's possible that the valence electrons are different now because the valence electrons which were outside are now inside. The core electrons become the valence electrons. The protons are still there, right? They're still the same. You haven't changed that. So what happens is the effective nuclear charge is now higher in cation. So if the effective nuclear charge is higher, then the cationic radii is smaller than the corresponding metal or element. In an anion, it's the other way around. Anions have accepted electrons, so when you have more electrons, but not enough protons for the attraction, it means that the size will get bigger for the anions. Okay. The easiest way to think about this, okay, and I hope nobody takes this personally in any way, but cations, once they lose electrons, you can think about them like losing weight. And if you lose weight, you get smaller. Anions, you eat up electrons, not you. Okay, let me say I. So when I eat up electrons, I will get bigger. That's kind of what's going on here. Okay, so here is your little bit of a diagram to see that. So lithium, when it loses one electron, look at the change, because one valence shell is completely gone now. Sodium becomes smaller, potassium becomes smaller. Now, between potassium and calcium, which are next to each other, because calcium loses 2 electrons and has more protons than potassium, the size is even smaller than potassium. So you lose more electrons, you get smaller. Look at aluminum, so small. Okay, so more electrons are lost and the smaller the cation size gets. But the cations trend down a group is still the same, which means that the size is increasing. I don't give this on the periodic table because the trends are not equal. This is for the cations, but look at the anions. In the case of fluorine, which becomes fluoride, the size is bigger. Okay, chlorine becoming chloride, size gets bigger. So sulfide would get even bigger, which is on the left-hand side. Phosphide would become even bigger. So size increases as you increase the number of electrons, okay, in there. So I don't write the ionic radii trend on the periodic table because it's not trending the same way. The trend going down is fine because that's still the same, okay, because within the same group you're adding on the same number of electrons, right? 1, 1, 1. Or you're losing the same number of electrons. So the radii remains the same, but across it's not the same. Okay, so you just kind of have to use your knowledge of how the number of protons and electron balance is changing. Okay, and effective nuclear charge is changing for that. Okay, so let's look at a problem for ionic radii. And this one seems to be all about anions. Okay, so let's look at the anions and see where they are on the periodic table. You remember that this is the number of protons. Okay, so this is the atomic number, so it's number of protons. So here's selenium, and then we have tellurium below that, both of them with the same valency. And then bromine here is the bromide, okay, which is 1 negative. Okay, so remember, as you go down, the radii increases, whether it's 2 minus or 3 minus, although it's not going to change, okay, because in the same group you're going to have the same charge. So as you go down, size increases. As you go to the right, in this case, you don't have a trend, okay, so you need to kind of pay attention to how many electrons are there in the anion. So selenium has 2 electrons, bromide has 1 electron. So 2 electron means that the imbalance is more between the electrons and protons. So here the effective nuclear charge is less. Okay, so which means this is the largest, this is the smallest. Okay, so here I think I must have explanation here for you. I do. So tellurium is larger because it is below, and then selenium 2 is larger because it's in the same row, accepting more electrons than bromine. Okay, that's kind of the key thing there. So that's your trend. Okay, now let's look at the ionic radii. Here we have a mixture of cations and anions. Okay, so let's go ahead and draw them all out. And the reason I'm drawing them out is just to see their number of protons, okay, in here. So if you look at all of these, it seems like they are all isoelectric. Okay, isoelectric meaning that they have the same number of electrons. If they have the same number of electrons, really we need to pay attention to the effective nuclear charge. Okay, so first we can keep it simple also, in the sense that if you have a cation, it's going to have a smaller size. If you have a dication like this one, which is 2 valency, so 2 plus is going to be smaller than 1 plus. Between phosphorus and chloride, so phosphide and chloride, phosphide has accepted 3 electrons, So if phosphorus, sorry, I should say phosphorus has accepted 3 electrons to become phosphide, then here the effective nuclear charge is more imbalanced. So this is bigger in size than chloride. So you can probably see where I'm going with this, right? Largest size, smallest size, because this one has given the most electron, this has accepted the most electrons. Okay, that's kind of how I'm thinking about these 4 ions, okay, in there. So here's the explanation. K plus is larger than calcium 2 plus. That's because effective nuclear charge is more for calcium ion. Again, the number of electrons and protons will show you the imbalance, okay, that's going on. And then here is the one for phosphorus, because phosphorus is going to be larger, more imbalance there, okay. So then here we have our trend, okay, for the ionic radii. So again, just keep in mind about the electrons and protons and the effective nuclear charge, the attraction between electrons and protons, valence electrons, okay, and protons, and that should help you with answering your questions. Here is a table with all the trends, okay, in there. So it's just a nice pictorial. You can make your own with your own color coding. I think that would be good. But otherwise, here are all the trends, okay, that we have. You will see the trend that's not there is the ionic radii, because that doesn't have a trend except for going down, okay. It is still getting larger. But everything else, there is no trend, okay, in there. But all the other ones, they're all trendy. They're all here. Okay, so a few things more to talk about in this portion. So one is that I mentioned to you a little bit before, that when you have metals and they form oxides, then they will actually give you bases, and then the non-metals, which is on the right hand side of the periodic table, they will give you acids. Okay, so that's why we kind of, you know, it's the most basic classification we do on the periodic table: acids and metals and non-metals, because they have very specific properties, you know. And so acidic property and basic property is also one of those. So metals give bases and non-metals give acids. Here are just some of the reactions so you can see how it's working. If you take a metal oxide and dissolve that in water, you end up getting sodium hydroxide. For example, here, sodium oxide. Okay, so giving sodium hydroxide. You take a non-metal oxide, dissolve that in water, and you end up getting sulfuric acid. You can do that with nitrous oxide or you know, carbon dioxide, anything that will give you an acid in water. So that is how it works. And I just need you to know this. You should be able to write the reactions also anyway. But even otherwise, at least you must know what gives acids and what gives bases, because I mean, we've learned about this already, okay, about acids and bases, that is. And then in the middle, you have the metalloids. Okay, the metalloids give you something which is called amphoteric oxides. And amphoteric is a word that means that something can behave like an acid or a base given its different conditions. Okay, so here is aluminum oxide, which is right in the middle, sort of in the middle, and it can react with an acid or a base. Okay, so metalloids kind of behave both ways. Okay, that's the interesting part about metalloids. So here are some questions on acidic and basic, and all you need to do is look at all of these and see which one is a metal and a non-metal. So aluminum is a metal, this is non-metal, this is metal, this is metal, this is non-metal. And that's all you're doing to figure out if something is give you acidic oxide or a basic oxide. Okay, so aluminum should give you a base in water, nitrogen dioxide should give you an acid. That's wrong. Okay, so yeah, I should correct that, and I will correct that as well later on. So that is acid, okay, in water. And then iron oxide should of course give you base, okay, in the water. And what else do we have? Calcium is a metal, should give you a base. Carbon should give you an acid, okay, in water. So that's how it goes, and that's how simple you want to keep this. So now I just want to talk a little bit about the individual groups and some of their properties. Okay, We don't get to talk about each individual element. Okay, you do that more when you get to inorganic chemistry, and really all the elements are really interesting. But as a group, I can just give you some properties, okay, some general things, and that's all this is. So group number one, which is the alkali metals, first of all, they are all metals. They're never found in nature in elemental state because they're very reactive. Okay, so potassium, rubidium, none of these elements are found as it is in nature. You can find them in compound form, right? So for example, in the ocean water, that's all sodium chloride. You'll have potassiums also in there in ionic form. So you can only find them in ionic form. Okay, that's really what it means. So everything is very reactive. But the interesting thing about that, about these metals, is once you do have the metals, then they're very soft actually. Okay, so if you have sodium, for example, potassium, lithium, all of these, you can just actually cut them with a butter knife. Okay, they're so soft in general. So that's their properties. Usually we say metals, one of the things that identifies a metal is that it's hard, but that's not true for group one. Okay, so never take anything at face value. You can learn the trends, but don't get so stuck in them that you're not able to open your mind and say, oh, okay, this might be different. Okay, and so these metals are a little bit different. All right, group number two, these are called the alkaline earth metal because you do find them in the earth everywhere. Any soil sample that you take will have magnesium, calcium, strontium, barium. All of these elements you will find in earth. Again, a lot of these are reactive metals. You don't find them as it is in nature. You will find them in compound form, but they are kind of more stable than group one. Okay, so you can isolate them and keep them in the lab. These ones are harder. You have to store group one in petroleum products so that they don't react with even air. But group two, even though they react with air, it's such a slow reaction that you can still work with some of these elements. Okay, so that's group two. Group three is a little bit boring, but group three, you start with a non-metal, then you go to a metalloid, and then these are a little bit more metallic in nature. All right, so we have all sort of three types of classification starting from group number four. Okay, the most common element that you are aware of is aluminum, and aluminum is very stable also because we have it in our homes as aluminum foil. Okay, and so it's quite a stable element, and we know it's quite flexible also. So that is group number three. Then we'll go on to group number four. Group number four, I gave its own slide because I really like group number four. And group number four has a lot of interesting elements in there. Okay, it has carbon to begin with, then it is silicon, germanium, tin, lead. Okay, I don't know what FL is. You don't remember that. But anyhow, the first few elements are really, really interesting here. Okay, so first of all, carbon is like the biggest component here, okay, which makes up the entire world because all the organic substances are made up of carbon. We are made up of carbon. We are carbon-based, I don't want to call it substances, okay, but beings, okay. All the plants, nature, everything is made up of carbon. So carbon really exists, okay. And by the way, just for an interesting kind of question, and you can email me with the answer without checking on the internet if you could, which element is in the highest percent on the earth? Which element? Okay, and it's not carbon. Okay, I know everything is made up of carbon, but it's not carbon. Okay, so which element is the highest percent on earth? All right, so you send me the answer. Okay, don't look on the internet. Okay, the next element down here is silicon, which is now getting into the metalloid category, and all the electronics are made out of silicon. Okay, and there's a whole Silicon Valley after silicon. So again, another very critical and important element. Then by the time you get to tin and lead, these are now metals. Okay, so group four is actually very interesting. Germanium here is also very interesting because of this, the electronics have become very good. And so when you get to physics, you will learn about semiconductors and whatnot. And that's where the metalloids are really interesting. Okay, and they make for really good electronic materials. One thing I want to talk about carbon is that carbon exists in 3 allotropic forms, and all 3 of them are so interesting, and that's why I want to talk about it for just a minute, okay, or so. So what is an allotrope? Allotrope is the same element but with a different molecular structure, okay? So the 3 molecular structures that carbon has is diamond, graphite, and yes, I knew you know this one also, Buckminster fullerene, all right? Diamond is considered to be a C4 kind of a structure, and this is what it would look like. C4 meaning tetrahedral, okay? Graphite is considered to be a hexagonal, so you have layers and layers of hexagons, okay, like this. And then Buckminster fullerene is like a ball, and it's like a soccer ball, okay, pretty much. And this literally was found, I think, only discovered 20 years ago on Earth, and it was made in the lab, but otherwise you find it actually in space, okay? It doesn't occur naturally on Earth. So what is so interesting about these? Number one, diamond is one of the hardest elements out there, okay? Very hard. Only a diamond can cut a diamond, okay? And so you know where we find diamonds also, right? It's found in mines, so you have to mine it out, which means it's formed under great pressure. Graphite, on the other hand, is such a soft um, molecular structure, you can actually write with it. Graphite is what is in the pencils. Lead is not in the pencil. We call it lead, but actually lead is not lead as a metal. Lead is actually the graphite. So you're right, when you write with pencil, you're actually leaving a layer of graphite, okay, on your paper. So that's graphite, very soft, okay? People do sketches with pencils. And then Buckminster fullerene is a whole other thing. Buckminster fullerene, by the way, gets its name from Buckminster, who was the one who designed the geodesic dome in Disney World. Okay, that's the Epcot Center. Okay, so if you look at that and then you see there is a resemblance, okay, in there. And this one literally is just completely out of this world, okay, because again, as I said, it does not exist naturally in Earth, so we have to make it. And now it's finding a lot of electrical uses. So carbon, it's not just that we are all made of carbon. There is just so much more to carbon than what we can see. Okay, so I can go on and on. I won't. Okay, I'm going to stop right here because we need to go and talk about group number 5. So, and group number 5 is boring. Okay, I'm sorry about this. All right, but otherwise there's nitrogen, there's the metalloids, and then there's metals also. Group number 5 also has all the 3 types of elements in there. Now, nitrogen is a very common gas, and it's found in the atmosphere, okay, and it forms a lot of oxides, and it's acidic in nature, right? Nitric acid is coming from, nitrogen oxides, but otherwise there is not much going on, okay? Arsenic is different because arsenic is a poison, okay? So we know about arsenic a little bit, but and if you want to watch the movie Arsenic and Orlace, really, really fun movie to watch. Anyhow, okay, group number 6 also not so interesting, but oxygen is there and we can't live without oxygen. So that's that. Again, these are non-metals, metalloids, and then by the time you get to the bottom, these are all metals, okay? Halogens is an interesting group because they're very reactive, first of all, okay? We do use halogens a lot in our lives, okay? One way or another, they're all around us, okay? We just don't realize it. So, fluorine is part of Teflon, for example, which is a non-stick. Chlorine is used as a disinfectant. Bromine probably we don't use as much, okay? But then iodine also is a disinfectant. These are all diatomics. So this is pretty much also a non-metal group, okay? At then becomes a little bit of a metal, but otherwise most of these elements are non-metals, okay, in general. The other great trend for halogens is that these two are gases, when bromine is a liquid and then iodine is a solid. So it's really an interesting trend here. In group number 6, oxygen was the gas, then sulfur is a solid. In group 5 also, nitrogen is a gas, okay? So here we have gases and then we are going into solids. Higher molecular weight or atomic weight gives you more solids. And then the last group that's remaining is group number 8, which are the noble gases. I didn't put them separately for any interesting reason. I didn't have any space in the previous one. Otherwise, I would have put it there. But otherwise, really, they're very, very boring because they don't do anything. They don't react. They're the noble gases, right? Noble people, okay, noble gases don't like to mingle with other elements. They are quite unreactive, but you can actually form some compounds, okay? So the only way we know of any of these gases is when we see them as in, oh, helium we fill balloons with, and neon, yes, we know about neon signs, and the only reason we know about krypton is because Superman is from there. Other than that, we don't know anything. Radon, you should explore a little bit more because radon is a very heavy gas, and radon is also radioactive, and radon does go under the earth and it travels in the earth. And the problem with radon is it goes everywhere and it's very toxic. It's carcinogenic, meaning it causes cancer. So this is one thing that people do when they buy houses, is to check for radon, okay, and make sure that there is no radon in their homes, okay. But anyhow, that's group number 8, and I think that should be it, hopefully, for this. Yes, so there was a lot of stuff, okay, there's a lot of stuff, I know, but hopefully all interesting stuff.